Okay. Any questions to start with on hybridization? We're going to finish that up and then we'll move into resonance structures. I know there's the part J, 1.2.2.J, which I don't quite understand what the point of that is myself. So we'll talk about resonance structures today, and then maybe a little bit on Wednesday. We can finish that up. I will on Wednesday give you some graded problems that'll be due for Friday on hybridization. And in your website, I do have some practice problems with the answer keys that I will go ahead and I'll release those after class. I think I released the mornings, but not the afternoons. It will be. These are problems I write myself, so they will be on Canvas. They're there. I just have to push the button and release them. So I will do that. Okay. Any questions about the hybridization first, and then we'll move into resonance structures. Okay, let's finish up the idea of forming the hybrid orbitals and the promotion with SF2, SF4, and SF6. And you get into the idea of expanded octets and where they come from, just so that we're all on the same page. You may have talked about this in general chemical principles, or the general chemistry class you took previously, but I want to make sure we're all on the same page. So let's start with SF2. And for SF2, I would write, first of all, for sulfur, the valence electrons are going to be in the 3s, the 3p orbitals. And so we're going to have 2 in the 3s, 2 in the 1,3p, and then 2 unpaired. So this is different than carbon. This is more like oxygen. Sulfur's right under oxygen on the periodic table. So instead of 2s and 2p's, we have for sulfur 3s and the 3p. Let me just move that over a little bit. Okay. So that means that to bond the fluorines, I need 2 unpaired electrons, which I have in the ground state. So for the sulfur, it's going to have 2 lone pairs and 2 unpaired electrons in its Lewis dot structure. And if I'm going to add fluorine to it, I know that fluorine has 1 unpaired, 3 lone pairs. So an SF2 molecule is basically going to pair up those 2 sets of unpaired electrons, and I'm going to form SF2. Okay. So I have a couple questions to ask. My first question is going to be, what is the hybridization of the fluorine? And your choices are A is SP, B is going to be SP2, and C is going to be SP3. So hopefully everybody has their cards. If you don't, I have various extra cards up here if you didn't bring them. Hopefully my phone still has juice in it. So that the question is, what is the hybridization of the fluorine? SP, SP2, or SP3? And I think that one. Okay. All right, so let's see what all right. So that's question number 1. So what you want to do is, you got to transfer, hold your card up. And if you're in the back and not in my direct line of sight, you might have to hold it up a little bit higher. Did I explain how these work? No. Okay, that makes the confusion. Okay, card. Sort of a Rorschach. There's a number on it. You don't have to worry about that because I haven't correlated anybody's name to number. So it's totally anonymous. There are letters on each side of the square. There's an A, a B, a C, and a D. So the side with the letter that's up is your answer. So if you want, for instance, this one is C. If I want to answer C, this would be how I would hold it up. If I wanted it to be D, it would be like this, and then like that, and like that. So the letter that's up is your answer. Okay? Now, notice that the cards are randomized so that you may be holding up the same letter like this as somebody else is like this. So unless you're like peering at their card, you're not going to know necessarily what they're holding up. Okay, so that's how we use the cards. Right, so you first of all, whatever your letter is, and then you hold it up. Then I scan it with my phone, and then I get a tally. So this is a clickerless clicker system.
It scans all of them and it just gets
Yeah.
a tally? That's cool.
Yeah. So I don't have to drag around boxes of clickers. You don't have to pull your phone out and, type anything in. You just hold them up. That's why I use it. So if anybody is doing, like they had the We the People program at one point, and a student who was helping with that was going down to the schools, the middle schools and stuff, you can just print these out, put the app on your phone, and you can use it. So they were like, can we have some of those cards? Because we go to schools that don't have like clickers, and it'd be helpful to get students involved. And so they are free, and they have funding, so they're never going away. Most free resources, if they don't monetize them, they disappear. Anyway, what's your answers? So you want to hold up your card, and then I will scan through. So I think the name is on there. These are called plickers, Plickers. Okay, let's see what I've got. So I've got 12 A's and 23 B's. And that's like 35, so maybe there were a couple that didn't get picked up, but I think there's 37 total. Okay, so normally what I do at this point is, if I have a little bit of a separation like this, I will grab one of my timers, my 1 minute timer. Where did I put my 1 minute timer from this morning? There's my 5 minute timer. There's my 1 minute timer, and I will say, discuss with people around you for a minute, and then we'll revote. So discuss, and then we'll revote. Like what did you put? Why? Okay, so now let's go ahead and revote. If you're in your discussion, you changed your mind, you can change your answer. If you didn't, then you didn't. And we'll revote, and we'll see where we end up now. And see, the thing is, you can't really tell how other people are voting. So this makes it kind of anonymous, as opposed to if I ask a question like, if I asked a question, then everybody's like looking around before they put their hand up. So that eliminates this. Okay, so now we're at 5:32. So we moved a little bit towards SP3. Okay, what is the hybridization of the fluorine? It's going to be SP3. Why? Because remember, it's the number of lone pairs plus the number of single bonds gives you the number of hybrid orbitals. And so in this case, For fluorine, I've got 3 lone pairs, a single bond, so that's 4. So how do I get 4? S and 3 Ps. So fluorine is sp3. Okay, so we just use that formula we talked about on Friday. All right, so now let's do this again with the sulfur. So what is the hybridization of sulfur? Same thing. SPA, 2B, sp3C. Bless you. So what's the hybridization of now the sulfur? All right, let's see what we have. Okay, we've got two SPs, two sp2s, and then 33 sp3s. So this one is sp3, 2 lone pairs, 2 sigma bonds. It's also sp3 hybridized. Okay. All right. So whenever I give you a Lewis dot structure and ask you to kind of like sketch the orbital picture of this, what you're going to have to do first is figure out what the hybridization is. And that's where the equation of lone pairs plus single bonds equals number of hybrid orbitals. That's how you determine hybridization. Okay, and that's the first step. You won't have to do carbocations or radicals, because what this book likes to do is it likes to foreshadow a lot of things. And when it does that, by the time we get the radicals later on in the semester, if I go, remember we talked about this like in the first week of class, and nobody remembers. So their foreshadowing attempts, I think, are not particularly useful. So that's why a lot of things we'll come back to, but dwelling on them right now isn't going to be helpful, is what I found. Okay, so what does that mean? That means that for the sulfur, what did I do? I hybridized those s and the 3p orbitals. That gave me 4 sp3 hybrid orbitals. Remember, we always hybridize orbitals first and then put the electrons into those. So an sp3 for carbon, because carbon has 4 unpaired electrons, that's what goes in the orbitals. For sulfur, what goes in the orbitals? 2 lone pairs and 2 unpaired. Okay. So this is like the 1s1, 1s2, 2s2 electronic configurations. Those are always blank, and then you fill them in with a particular element. The same thing is true here. An sp3 hybridized atom is going to be tetrahedral. So the sulfur is then going to be tetrahedral, 1, 2, 3, 4 lobes of electron density. What goes in those? 2 lone pairs. They can go in any of the orbitals. And then an unpaired electron in each. And so then the fluorines are going to come in. The fluorines are also sp3 hybridized. So there's 1 fluorine. There's 2 fluorines. 3 of the p orbitals have lone pairs in them for fluorine. And then 1 in each, and that's what's going to form the first sigma bond, and that's what's going to form the second sigma bond. So this would be my orbital picture for SF2. And it may seem kind of like, I don't know, this may seem kind of dumb, but it doesn't matter whether you put the dots in or outside of the orbital. It doesn't matter. But sometimes that people will ask, well, do they have to go inside or outside? It doesn't matter. You know, if I was drawing this really nicely, I would have made sure they go inside, but as long as they're close. Okay, so there's SF4. Or sorry, SF2. Now we want to do SF4. So first of all, SF4, I'm going to have a problem because I need 4 unpaired electrons to bond the 4 fluorines. And in the ground state electronic configuration of sulfur, I only have 2 unpaired electrons. So I'm going to have to promote something. So let's go back to sulfur. I've got a 3s, I've got a 3p, and so I've got my pair, my other pair, and my 2 single bonds, or 2 single unpaired electrons. Okay. So I need to promote to a higher orbital, but what is the higher orbital? What is above a 3p? There's no 2d orbital. If there was a 2d orbital, we could form expanded octets with carbons and oxygens. There is no 2ds. 4s. Remember, the 4s is above the 3p. So if I sketch out kind of my periodic table, one of these days I'll hang up a periodic table in some of these math rooms and then they'll tear it down. But if you remember, like over here is where the S's are, these are where the D's are, and those are where the P's are. So once I fill up the 2p, I go to the 3s, then I fill up the 3p, then I fill up the 3p's, then I go to the 4s, and then I'm in the 4d's. Or sorry, 3d's. Because these are always, the transition metals are always one behind. So I've got a 4s. Well, I'm going to have to add some energy to this system to go into an excited state, just like I did on Friday. Now I'm hoping to get that energy back by hybridizing and forming more bonds. But the quantum mechanical rule says you cannot hybridize orbitals that have different principal quantum numbers. So in other words, I couldn't form an expanded octet for carbon because I can't hybridize a 3s and 2p's. They don't have the same principal quantum number. So that means I can't hybridize 4s and 3p. So now I have to ask what's above the 4s. That's the 3d. So now above the 4s, I've got 5 d orbitals. And so now I can promote this up to the 3d. So I can go ahead and promote that electron up there. And I probably shouldn't write it there, but I can promote it up there. Why? Because now I can hybridize the 3d, the 3p, and the 3s. So quantum mechanically, you're not allowed to hybridize orbitals that don't have the same principal quantum number or the same shell number. And so having access to that 3d now means that in the excited state, I can now have 1 unpaired electron in each of the p's. I'm going to skip the 3 or the 4s and just go directly to the 3d. So now I've solved my problem of having 4 unpaired electrons to form SF4. Now I can do that. But of course, I'm going to hybridize these orbitals. And so what I'm going to hybridize is I'm going to hybridize the D, the S, and the 3Ps. So that means I'm going to end up with 5 DSP3 or SP3D hybrid orbitals. I don't care which order they come in. Okay. But I'm always hybridizing the orbitals first. Okay. So now I can hybridize 5. Because SF4, if you think about how am I going to form my Lewis dot structure for SF4, I'm going to go 1 fluorine, 2 fluorines, 3 fluorines, 4 fluorines, and that's going to leave me with a lone pair and 4 sigma bonds. It means I have 5 hybrid orbitals, 5 hybrid orbitals. What goes into those 5 hybrid orbitals for sulfur? A pair, and then 1 unpaired. Okay, so form the orbitals first, then put the electrons in it, depending on the atom. Got to go to Vesper Theory and say if you have 5 lobes of electron density around the sulfur, what is that geometry? And it's trigonal bipyramidal, so that means the sulfur is going to have 5 lobes of electron density. Where does the lone pair go? I forget which place, whether it should be in one of the linear positions or one of the trigonal bipyramidals. Actually, that's a level of detail that if you needed to know, you would just look up in your general chem book, like which one of those is most stable. I think I remember them going here, but if I am wrong, I'm wrong. Okay. So we put the lone pair there, then we would take our fluorine, our sp3 hybridized fluorines, and then we can go ahead and sort of sketch out the picture like this. And then again, there'd be lone pairs all the way around. And then unpaired electrons every place I'm forming my sigma bonds. And so there'd be a sigma bond there, a sigma bond there, a sigma bond there, a sigma bond there. So this gets to the general chemistry principle. And I don't think I asked you on Friday, but if I would have asked and said, what elements are allowed to have an expanded octet? You probably would have said, oh, sulfur, phosphorus, and I would have said, no, I'm talking about general principles, what elements can have expanded octets, and then you would have said, oh, all elements in row 3 or lower can have expanded octets. So the question is, why does it have to be row 3 or lower? Because at row 3 or lower, we have a 3D orbital that we can promote into and hybridize. It's not just good enough to promote, it's got to be promote and hybridize. Because if I'm going to invest in the promotion with energy, I need to get that back. And the only way I get it back is a combination of forming bonds and hybridizing. That's how I get it back. So that's how we can promote the sulfur and how we can make a dsp3 out of it. All right. Everybody kind of with me so far? So then the remaining one, just to kind of complete this story, is SF6. So if we go SF6, I'm still going to have my 3p, my 3s, my 3p, and then my 3ds. But now what I need to do is, if I start with my first excited state, I've only got the ability to form 4 bonds. I need to form 6. So now I'm going to take this electron and now promote it up into the second d orbital. And when I do that, now I'm going to end up with 6 unpaired electrons spread out over 6 orbitals. And so now I can say, okay, there's my 6 orbitals that I'm going to hybridize. I'm going to hybridize 2 Ds, an S, and 3P to form a D2sp3 or sp3d2, whatever. And for SF6, those 6 hybrid orbitals each have 1 unpaired electron in each. And so now if I'm looking at that sulfur, I can say 6 lobes of electron density around a sulfur is what kind of geometry? It's going to be octahedral. And so now I'm going to have my 6 lobes which are going to be like the X, Y, and Z coordinates, only now they're going to have one electron each. So SF6 is going to have an octahedral geometry. And then I put my fluorines in. So again, the whole idea here is, first of all, we have to figure out the hybridization. If I give you a structure, you're going to do that by the number of lone pairs plus the number of sigma bonds. That gives you the number of hybrid orbitals. Once you know the number of hybrid orbitals, it's going to be anywhere from 2 to 6, sp to d2 sp3. And then once you know that, you can sketch out the atom, the geometry of the orbitals. Given that atom and the number of lone pairs and single and unpaired, you put those into the orbitals, and then you form your picture. Okay, so this is where the expanded octets come from. Okay. All right, so does that make sense to everybody? Okay, just me asking is not good educational practice. I should follow up with a problem, which I will do on Wednesday or at the end of this class. Or you will follow up by some of the practice problems I give you. Okay. So that kind of finishes up the hybridization, the basics. The hybridization as it relates to the resonance structures, I gave you the easiest cases I could, because after that I actually had another whole part written, and then just like in the middle of recording it, and I'm like, wait, no, I need to stop because this just isn't going to make any sense. So the key with the hybridization is that we really would look at the hybridization of the resonance hybrid. And the resonance hybrid is going to have sort of a bizarre type of hybridization. So the one thing we can say for certain is that all of the atoms have to have hybridizations that do not make them move. Remember, there's a whole thing about resonance structures anyway, of the resonance structures themselves aren't real, it's the hybrid that's real. And so having the resonance structures, is it possible that an atom may be sp3 in one resonance structure and sp2 in another? It's actually possible, but those two hybridizations then don't cause the oxygen or whatever atom to move physically in space, because all I can do is move pi electrons. I can't move atoms in resonance structures. Okay. Right. So what I want to do is have us draw out an example of some resonance structures and then go through the rules to figure those out. So let's say that I have an O, a C, and an N, all attached together, and overall that has a -1 charge. So I have to tell you the number of resonance structures I'm expecting you to draw, and I also have to lay down the following rule is that for these kinds of problems at the beginning of this of the course, all of the resonance structures are going to have atoms with completed octets, for the most part. If I violate that, I certainly will do so later on, because a C plus cannot have a completed octet. A C dot, the radical, cannot have a completed octet. So whenever we have those kinds of structures, they don't have completed octets. Do they have valid resonance structures? Yes, but we'll get to that. Okay, so OCN, there are 3 resonance structures that we can draw for this. What I'd like you to do is to draw one. Okay, draw one valid Lewis dot structure for OCN minus. Okay. And so how are you going to do that? How many valence electrons in a neutral oxygen? 6. How many in a carbon? 4. How many in nitrogen? 5. I got a -1 charge, so what do I need to do? Add an electron. Where? Anywhere. Just don't lose them along the way. Don't add any more than 1 and don't lose any. Okay, so draw a structure, draw a Lewis dot structure of OCN minus. And if you draw 1, try and draw all 3. Give you about 5 minutes or so to do that. And then if you got all 3 of them, then you can try and rank them, although we will do that. And you can discuss with people next to you. Normally I would be walking around, but I can't fit it in between the aisles. So that means I'd be kind of lurking around the edges and not making it into the middle. So we're starting with 6 on oxygen, 4 on carbon, 5 on nitrogen, and then an extra one, and then you're going to make your bonds to give you octets for everybody. So if you have all 3 of them, then you can go ahead. Let's see which ones are. Got one more. Yeah.
So like first, like,
Is it in like?
let's like try it on your own.
Oh, okay, so then people actually try it out.
Yeah. So like,
It's not used to that.
but you'll draw like a partial bond. Give them another couple weeks.
Another day.
So like for these ones, see how early I should go. But for like this and it's either done one symbol and then a partial.
Okay, so since hopefully everybody has one, so let's somebody give me one at a time. So who wants to volunteer? I could pull out my iPad and we could randomize that, but apparently that stresses people out. That's why we use Piazza. Okay, let's go for, yes, what do you have? How many lone pairs on the oxygen?
One.
One lone pair on the oxygen. What kind of bond between O and C? And lone pairs on carbon? Bond between C and N? How many lone pairs on nitrogen? Formal charges. Formal charges on these atoms. What do we have, Hannah?
Plus one on the oxygen.
Okay.
0 for carbon.
Okay.
-2 on nitrogen.
Is that correct? All right. And go gentle if it's not quite correct. Right. Don't be harsh because you'll be in a harsh position later on. Okay. How do we do, Lewis? How do we do formal charges? So there's a formula we can use that's basically the number of electrons in a neutral atom minus the number of lone pair electrons minus the one half the number of bonding electrons. The only tricky thing about the half of the bonding electrons is that you have to realize every bond is worth 2 electrons. So you can use that formula. I kind of use a more intuitive approach, which says oxygen came with how many electrons? As a neutral atom, it came with 6. How many electrons does that oxygen own right now? Now, how many does it share? Technically, it shares like 8 or 6 or 8, depending on how you define sharing. From the oxygen standpoint, it's got a completed octet. It's definitely sharing 1 in each of these 3 bonds. It owns the lone pair outright. So my question is, it came with 6. How many does it now own? It owns the lone pairs outright, and it owns half of every bond. So it owns 5. So going from 6 to 5, what happened? It lost an electron, so it's a +1. So that's sort of the intuitive way I do it. If we looked at the nitrogen came with 5. It owns 6 outright. It owns that one for 7. Came with 5. It now owns 7. It's picked up 2, -2. Okay. So that's kind of the intuitive way I do it. And again, each bond is shared, but if they split amicably, each atom would get 1 electron. So that's how I determine ownership. Okay. Okay, so that's number 1. How about another one?
So the oxygen has 3 lone pairs,
Okay,
and then a single bond between oxygen and carbon,
okay,
triple bond between carbon and nitrogen, and then 2 lone pairs on nitrogen, or one lone pair.
okay. Let me write down 2 because that's a mistake that you could make. And we need to talk about how do you double check your answer. Okay, so if somebody wrote this and I said, does that look okay? And you'd go, maybe not. So here's what you want to check. Number one, you want to check and make sure that each atom has an octet and only an octet. If it can form an expanded octet, that's great, but oxygen, nitrogen, and carbon cannot form expanded octets. So as soon as I look at this one, I see 2, 4, 6, 8, 10. No, not happening. So that means I've got an extra lone pair in there. Now, if I have an extra lone pair in there, the charges will not add up to what they should. So we check first for octets, and then we look at the formal charges, make sure they're done correctly, and then make sure they add up, in this case, to -1. So in this case, the formal charge on the oxygen would be -1, carbon,
0,
and nitrogen, 0. So the only one that has a negative charge is oxygen. Okay. So you're kind of looking, oh, that's the opposite of the first one. I guess. In terms of placements of triple and single bonds and lone pairs, it might be the opposite. But remember, what I'm doing is I'm moving lone pairs around. Okay, third one.
I have oxygen with 2 lone pairs.
Okay.
A double bond to carbon,
Okay.
which has no lone pairs, and then it's double bonded to nitrogen, which has 2 lone pairs.
And formal charge.
0 for oxygen, 0 for carbon, -1 for nitrogen.
Does that one look good? Did anybody have any other ones? I mean, I always ask that and see how creative people are. At this point, if you're creative, you're probably wrong. But again, you want to check each one of these. Okay, so I've got 3. I've got A, and I've got B, and I've got C. So here are my 3 resonance structures for OCN minus. And the question is, are any of these the true structure of OCN minus? And the answer is no. These are all resonance structures. So the true structure is the resonance hybrid. And the resonance hybrid is going to be the average of these 3 structures, sort of the numerical average. So before we write the hybrid, we need to rank these according to stability, which means we need our stability rules. And so rule number 1 is we have completed octets. And typically I'll ask you only to write resonance structures with completed octets. So that's usually a given. Number 2, well, actually I think I called this 1B. 1B would be that the best case scenario would be all 0 formal charges. But that can't happen in this case because I got a -1 ion. So that's not happening. But number 2 then, I want small charges of ±1 versus, let's say, ±2, or, I guess, a small number of charges. And which one, that's kind of hard to tell sometimes. Now, these are sequential rules. So we apply rule number 1 and see if we can make a judgment. Then anything that's tied, we go to rule number 2. And then anything that's tied, we go to rule number 3. So in this case, all of them have completed octets, check. 0 formal charges can't happen, check. Small number of charges, does that eliminate any of these or make any of these the least stable? A. So A is by far and away the least stable. Now, what does that mean to the hybrid? That means that numerically, what happens is the hybrid is a weighted average of all 3 of these structures, with the weighting factor being stability. So the resonance hybrid is going to look the most like the most stable resonance structures. Okay. So in this case, A isn't going to contribute very much to the resonance hybrid. So I'm actually not going to include it when I write my resonance hybrid. So sometimes in a problem I will say, write 3 resonance structures with completed octets, and then write the hybrid of the most stable 2. The reason I do that is because they're not all equal contributors, is the terminology. Okay. You can relate this to genetics somehow, but it's a math, like if you get 2 things. It's sort of that principle, but what it's really like is what contributes more to your grade in this class? Quizzes or exams? Exams, because of the weighting factor. The thing is, these 3 rules are very qualitative rules and not quantitative. If we want quantitative results, we have to use a computer in order to get the exact results. So we're going to do this very qualitatively. All right, so number B and C then, letters B and C are still tied, right? So now we need to go to rule number 3, which says that the electronegativities match the charges as best we can. And that's an overstatement of what was in the notes. Basically, that means that negative charges should go on the most electronegative element, and the positive charge would go on the least electronegative element. So in this case, the negative charge is going to be more comfortable on O or N. So here's our periodic table. We got a C, N, O, F. And the electronegativities move towards fluorine, because fluorine's most. So what's more electronegative? Oxygen. So that means this is going to be the most stable. And this is going to be the least stable. Nope. That's second. That's whatever you want. Second. Second least, second most, whatever. Okay. So then we have to do our hybrid. And so our hybrid has to be an average of charge and bond length. Okay. And so that's how we're going to do the average. And so we'll do that at the beginning of class on Wednesday. Okay. So for Wednesday, what I'd like you to do is to go over the next set in the reading list, which I think moves into chapter 3 or 2, I think. So whatever that reading assignment is, that's what we'll talk about. We'll finish this up. Any questions, either email me, post them on Piazza. I think I'm averaging a 1.6 hour turnaround time, which it lets me know, which I don't know why, because if somebody posts at 10 o'clock, you're not getting it at midnight. So, but if you have any questions, by all means, come see me, email me, or post it up on